Okay, so we discussed previously this idea of writing out chemical equations from text. So we know how to convert names of compounds into their corresponding formulas. So looking at the following example, we're asked to balance the following chemical equation. So the first thing we're going to do is we're going to highlight the keywords. So I see keywords such as solution. I see the keyword to yield, and I see some names. Okay, so now what I'm going to do is I'm going to convert the names into formulas. So copper 2 chloride, we have copper 2 plus. Chlorine as a 7A element prefers to adopt a -1 charge. We cross our charges and that gives you CuCl2. Since it's a solution, we in turn put the aqueous symbol. Next, when we have a solution of sodium sulfide, so we have sodium plus and S2 minus, we cross our charges and that gives us Na2S. Since it's a solution, we put the aqueous symbol. For copper 2 sulfide, we have copper 2 plus. Sulfur as a 6A element adopts a 2 minus charge. We cross our charges and that gives us CuS. Because remember, for ionic compounds, we want the simplest ratio of atoms. Next, we have sodium chloride, which is sodium plus and Cl minus. We cross our charges and that gives us NaCl. So we have solid copper sulfide and sodium chloride is aqueous because it's soluble in water. Okay, so that's the first step when you're writing chemical reactions from text. You need to convert the names into a formula. Next, now that we have our proposed formula, so copper chloride is mixed with, so that tells us to put a plus sign, sodium sulfide. To yield tells us that we need to write a reaction arrow. And then our products are copper sulfide and sodium chloride. Now, thinking about how we balance this equation, given looking at this equation, we have 1 copper, 2 chlorines, 2 sodiums, and 1 sulfur on the left. And we have 1 copper and 1 sulfur on the right, as well as 2 sodium, as well as 1 sodium and 1 chlorine on the right. In order for us to have the same number of atoms of each element, what coefficient do we need to use? What coefficient do we need to, quote unquote, guess for sodium chloride? What coefficient do we need to use for sodium chloride? In order to have 2 sodiums and 2 chlorines on each side, what coefficient do we need?
2.
2, exactly right. And that's all we need to balance this equation. So then we write out our final answer. So we have copper chloride or copper 2 chloride aqueous plus sodium sulfide aqueous leads to copper sulfide solid plus 2 sodium chloride aqueous. Does this example make sense?
Yes.
Perfect. So let's work on the following example, and I'd like you to start trying to convert the following sentence into a chemical equation. I'd like us to start by identifying the formulas of each of our compounds in this chemical equation. So let's start off by writing some formulas. And if you're finished writing the formulas during this problem solving session, don't be shy to start putting the formulas together into an equation using our reaction keywords. So let's get started with this example. Let's spend about 4 minutes first making sure we have all of the formulas written for each of the compounds in this chemical equation. And don't be shy to share your proposed formulas. And I'll put some labels A, B, C, and D. And don't be shy to share your formulas for each of these 4 compounds. And even don't be shy to try including your physical states for each of these compounds. And if you have any questions, don't be shy to let me know in the chat or verbally. And you can share your proposed formulas in the chat or using the annotate tool. And we have a proposed balanced equation with formulas provided. So this is our student proposed equation with formulas. So let's keep working on this example, and I'd like students to comment, do you agree with this proposed set of formulas and this proposed balanced equation? Do you disagree? Are there any differences in your solution? Do you have a different proposed formula for any of these compounds? Don't be shy to share your responses in the chat or verbally, or ask a question in the chat or verbally. And we'll discuss in another 2 to 3 minutes. What does everyone think so far as you're working through this example? Do your formulas match that proposed by this student? Do they disagree? Do you have another perspective on this problem? Don't be shy to share your responses in the chat or verbally. And we'll discuss the first part of this example in about another minute and a half. Okay, so let's discuss. Let's first unpack the formulas. So for lead nitrate, we have lead 2 plus, nitrate is NO3 minus. We cross our charges and that gives us PbNO3 2. We see the keyword solution. What does that tell us? What state do we put for a solution?
Aqueous.
Aqueous, exactly right. So for sodium chloride, we have sodium plus and Cl minus. We cross our charges and that gives us sodium chloride aqueous. The and symbol tells us we put a plus. Yielding tells us we draw a reaction arrow. Sodium nitrate, we have sodium plus and NO3 minus. We cross our charges, that gives us NaNO3. And what state symbol do we put if we have a solution?
Aqueous.
Yep, exactly right. We put an aqueous state symbol. One moment. There we go. So we put the aqueous state symbol. And for a solid precipitate of lead 2 chloride, so lead has a 2 plus charge, chloride is Cl minus. We cross our charges and that gives us PbCl2. And since it's a precipitate, what symbol do we put?
Solid.
Yep, exactly right. Perfect, perfect. So now that we have our blanket unbalanced chemical equation, I'd like us to figure out what coefficients do we need for each of these chemical species. So let's take about 3 minutes and let's try to assign the coefficients for each of the species in this equation. You're also welcome to share your coefficients using the annotate tool in the chat or verbally. So now that we've written out this unbalanced chemical equation, we're ready to start by balancing this equation to finish off this problem. So, wow, students are quite fast at this. We're already seeing some proposed responses for our coefficients. Let's give students a little bit more time just so that way we give many students in the class a chance to respond, formulate a perspective and a response for this example, and share their response. As that process of coming up with a response and then sharing it, articulating that response is really valuable for the overall learning process. So let's give everyone a little bit more time and let's keep working on this example. Keep sharing your responses in the chat as they're really helpful to help me gauge how to go about presenting the material in a way to address student concerns and questions. And we'll discuss in about another 1.5 to 2 minutes. And let's keep working on this example and we'll discuss in about another minute. Okay, so let's look at the following example and let's do some counting. So when you're balancing ionic equations, you can think about your counts in terms of atoms or ions. We'll stick with the traditional approach of counting atoms just to keep things simple. So we have 1 lead, 2 nitrogens, 6 oxygens, as well as 1 sodium and 1 chlorine on the left. And we have 1 sodium, 1 nitrogen, and 3 oxygens on the right, along with 1 lead and 2 chlorines on the right. So then, with that established, how many sodium nitrates do we need to get 2 nitrogens and 6 oxygens? What coefficient do we need for sodium nitrate? What coefficient would we need for sodium nitrate?
2.
2, exactly right. That in turn gives us 2 sodiums, 2 nitrogen, and 6 oxygen. So then, what coefficient do we need in front of sodium chloride now to balance sodium?
2.
2, yep. Perfect, perfect. And with that, chlorine's balanced, sodium's balanced, nitrogen's balanced, oxygen is balanced, and lead is balanced. So this gives us our complete balanced chemical equation with all of the state symbols added. Does that make sense? Any questions on this example? If not, let's keep going then. So I just provided more space if students needed it. So let's work on another example. This time I provided a table below for students to utilize the table method. So we have a solution of barium hydroxide and a solution of potassium sulfate are mixed, yielding a solution of potassium hydroxide and a solid barium sulfate precipitate. So let's look at the following example. Let's first try to write out the formulas for each of these 4 compounds. And once we have our formulas established, then we can focus on balancing our chemical equation. If you happen to have the formulas already written down, then you can then move on and try to balance the equation. So let's work on this first part for this example for about 3 to 4 minutes. This is part of why nomenclature is so important, because many times it's easier to convey a chemical reaction verbally with words rather than with a direct chemical equation. People like to communicate using structured sentences. So it's important to be able to convert chemical names into formulas and understand how to write a chemical equation given a sentence describing that equation. So let's work on this example. I'd like to see some formulas proposed in the chat or written out using the annotate feature on our class whiteboard, and we'll discuss in about 3 to 4 minutes. And if you have any questions, don't be shy to ask it in the chat or verbally. And if you have any questions that you're stuck, and if you have any parts that you need a little bit more clarification on, don't be shy to ask in the chat, and I'd be happy to answer your questions. We're already seeing students start to contribute their basic formulas for each of these different compounds. And if you're feeling adventurous, you can try adding the state symbols, as I provided hints for the state symbols in this equation. The responses I'm seeing for the rudimentary chemical equations are looking great so far. Let's keep working on this example, and then we'll discuss in about another minute and a half. But it's great to see students engaging with the material and sharing their perspective. And I'm just going to write out the student proposed chemical equation, unbalanced, oh, already balanced actually. So let me write that out, just so that way we all have a common frame of reference to continue our discussion. So we have a few student responses in the chat or verbal and presented on our class whiteboard. So do you agree? Do you disagree with these responses? Do you have the same formulas? Do you have different formulas? Don't be shy to contribute your perspective to this class discussion, and we'll discuss this example in another minute. Okay, so let's discuss the first part, which is just getting our formulas. So barium hydroxide, whoops. So barium is written as barium 2 plus. Hydroxide is OH minus. Crossing our charges, we have barium hydroxide. Since it's a solution, we put the aqueous symbol. Potassium sulfate, we have potassium plus and SO4 2 minus. We cross our charges, and that gives us K2SO4. Since it's a solution, we put an aqueous symbol. Yielding tells us that we draw a reaction arrow. Potassium hydroxide, we have potassium plus and OH minus. We cross our charges and we get KOH aqueous. Barium sulfate, we take barium 2 plus and SO4 2 minus. We cross our charges to get the simplest ratio of ions, and that gives us barium sulfate solid. Okay, we now have our rudimentary unbalanced chemical equation. Let's now focus on balancing this chemical equation. So what coefficients need to be adjusted or modified to balance this chemical equation? I provided you a table if you wish to use the table method. Let's take about 2 to 3 minutes and let's try adjusting our reaction coefficients to get a balanced equation. Don't be shy to draw out your proposed reaction coefficients. Let me label them for everyone's reference. So we have A, B, C, and D. Don't be shy to draw out your proposed reaction coefficients to balance this chemical equation. And if you have any questions or proposed responses, don't be shy to share them verbally or in the chat. So don't be shy to share your updated and balanced chemical equation coefficients. And we'll discuss this example momentarily. We already see students sharing their proposed balanced equations in the chat and their proposed modified coefficients. Let's keep working through this example and we'll discuss in about another 1.5 to 2 minutes. So we see many students in the chat are just proposing one coefficient change, which is the addition of a 2 in front of potassium hydroxide. Does everyone agree with that proposal? Do you disagree with that proposal? Do you have an alternative set of coefficients? Let's try to add on to this class discussion, and then we'll discuss this momentarily in about another 1 to 1.5 minutes. Okay, so let's discuss this example. So applying the table method, the student responses that I've seen with a coefficient of 2 in front of potassium hydroxide were perfectly correct. But let's talk about the reasoning behind this. So we're going to write out the formulas for each of our chemical species, and we're going to count our atoms. Remember, this subscript applies to both atoms in our parentheses. So now doing some bookkeeping and noting the number of atoms of each element. So now that we have our atom counts established, we see very clearly that potassium is not balanced. So in order to get 2 potassium atoms on each side of our equation, what coefficient do we need in front of potassium hydroxide? What times 1 would give us 2? 2, yep. So we get 2 potassium, 2 oxygen, and 2 hydrogen. So in turn, we see barium's balanced, sulfur is balanced, oxygen's balanced, and hydrogen is balanced, and potassium is balanced. So we now have our final balanced chemical equation with only a single coefficient needing to be changed. Does this example make sense to everyone? Perfect, perfect. Okay, so let's keep going now. I just provided some more space just so that way students didn't feel too cramped when working through these problems. Now, I'm going to teach you a trick that applies primarily to a subclass of reactions known as displacement reactions. This method of balancing equations is known as the half notation method. Some students like it, some students really dislike it. This is an optional method, but it certainly can make your life easier. Half notation is primarily useful. Your signpost for when you should start thinking about using half notation is when your reactions contain a pure element, such as nitrogen gas. Your first goal is to balance as many elements as possible by adjusting the whole number coefficients, starting from the most complex molecules, followed by the isolated elements. So in this case, we see that we have 3 hydrogens on the right. We have 4 hydrogens on the left. We are going to, in turn, utilize the least common multiple method. So that gives us 3N2H4 leads to 4NH3 plus N2. And with that least common multiple method, we see that we have now fully balanced this chemical equation. So that's one method of doing it. This is our good old friend, the least common multiple, or the quote unquote LCM method. The other method that we can use is known as the fractional method. And it essentially goes like this. We have 2 nitrogens on the left. We have 1 nitrogen on the right and 2 nitrogens from N2. That gives us 3 nitrogens. If we wanted to balance nitrogen, we are going to guess a fraction. We're going to guess a fraction in front of nitrogen. So we'll guess a fraction of 1/2, so that in total we have 2 nitrogens on each side. So another fraction that we could potentially guess in this case, is if we have 2 nitrogens and 4 hydrogens on the left, and we have 1 nitrogen and 3 hydrogens on the right, we can just as easily apply this idea of guessing a fractional coefficient by placing a fractional coefficient in front of N2H4 or NH3. Okay, so what times 3 would give us 4? We'd guess a coefficient of 4/3. And the trick for guessing a fractional coefficient, you put what you want on top, you put what you start off with on the bottom. Okay, so if we revise our counts now, we have 4/3 nitrogen, we have 4 hydrogens, and we have 2 nitrogens from N2. Okay, so it appears like we're getting somewhere here. So just like before, if we want our total number of nitrogens to match the 2 nitrogens on the right, we're going to now guess coefficients. We're now going to guess coefficients for N2. So we have 2 nitrogens times what coefficient plus 4/3 would give us 2. So another way to think about this 2 nitrogens, you can think about it as 6/3, okay? And another way you can think about these 2 nitrogens is that we have 6/3. Okay, so now we then guess a fraction that would give us a total of 6/3 nitrogen. So we guess a fraction of 1/3, which in turn gives us a total of 6/3 nitrogen. So we place our fractional coefficients in front of each of our chemical species. This equation, you don't get a ton of benefit from half notation, but once you have your fractional coefficients in place, so you're balancing the equation using fractional coefficients rather than whole number coefficients, you have to take one additional step to get your final equation. This equation is balanced currently in terms of atoms, but we cannot have fractional coefficients in our final answer. So in order to get rid of our fractional coefficients that we used to quickly balance our chemical equation, we're going to multiply all of our reaction coefficients by the least common denominator, which is the number on bottom. So we're going to multiply all of our coefficients by 3. And that in turn gives us the following balanced equation, which is identical to the result that we obtained using the least common multiple method. Now, for those that are curious, the reason why the least common multiple method works is that we are, in essence, balancing the equation using the half notation method and then multiplying out each of our coefficients by a whole number. So some students really find the half notation method efficient, and it really is a matter of the exact equation that you're dealing with. In this case, the least common multiple method is probably a little bit faster. Let's look at an example where the half notation method really shines. And these typically include reactions with oxygen. So looking at this equation, we have 4 phosphorus and 2 oxygen on the left, while we have 1 phosphorus and 3 oxygens on the right. Okay. So now what we're going to do is we're going to guess a coefficient. We're going to guess a series of coefficients. In order to have the same number of atoms of each element on each side of our equation. So then, let's try using the half notation method and let's guess a coefficient for phosphorus. In order to have 1 phosphorus on each side, if we start with 4 phosphoruses on the left, what fraction do we need to guess? We put what we want on top, what we start with on the bottom. So what fraction should we guess?
1/4.
1/4, exactly right. We put what we want, which is 1 on top. We put what we start with, which is 4 on the bottom. Does that make sense? Perfect. Let's look now at this oxygen. If we want 3 oxygens and we start with 2, what coefficient, what fraction do we guess?
3/2.
3/2. We want 3, we have 2, we put 3 on top, we put 2 on bottom. That in turn gives us the following atom balanced but incomplete chemical equation. Okay, so now that I have all of these coefficients established, what do I multiply each of my fractions by?
4.
4. Yep, you find the largest number on in our divisor, or in our denominator, and we multiply each of our coefficients by the least common multiple of our denominator. So in this case, the largest number on the bottom is 4. So we're going to multiply all of our coefficients. Note all of the coefficients by 4. And that in turn gives us P4 plus, so 3/2 times 4 gives us 6O2, leads to 4PO3. And as we can see, we have 4 phosphorus and 12 oxygens on each side. Anytime you see reactions involving oxygen, it's a great chance that likely the equation could be balanced efficiently using the half notation method. Does everyone see how the half notation method could potentially be quite useful for these types of reactions? Some students really like the half notation method, other students dislike it. It's just another tool to balance chemical equations. But if you choose the correct method of balancing a chemical equation, you can certainly save yourself a lot of time.
Professor, so why wouldn't the answer that would be circled would be the bottom one and it's the top one?
So the top answer is balanced in terms of atoms, but we can't have fractions in our coefficients because half a molecule doesn't have any physical meaning. So we want our chemical equations to convey what's actually occurring in terms of the species that are engaging in our chemical reaction. So as a solid rule for chemical equations, you never can have fractional coefficients in your final answer. But we can use fractional coefficients as a shortcut to get us closer to our final answer and to make it easier to balance our atoms at a first glance. We then have to fix the equation by getting rid of our fractions using a common whole number. Does that make sense?
A little bit. I guess I'll have to pay more attention on if we do another one.
So essentially, the top equation is balanced in terms of atoms, but per definition, we can't have fractional coefficients in our final chemical equation. So as a fix, we just simply get rid of our fractional coefficients by multiplying each of our coefficients by a whole number. And as we notice in our final answer, we have the simplest whole number coefficients. So we don't have any fractions, and they're the smallest possible numbers for this balanced equation.
Okay.
Does that make sense?
Yes, thank you.
Perfect. So let's look at another example. And this time I'd like you to try to balance the following chemical equation. I'll fill in the coefficients A, B, and C. And I'd like you to take about 3 to 4 minutes and try to balance the following chemical equation. And then we'll discuss momentarily. If you have any questions, or if you'd like to share your response, don't be shy to share your questions or responses in the chat or verbally.
Professor, I have a question. If we prefer one of the methods, like for
Yes,
example,
you're more than welcome to use that other method. There's
Okay.
no, as long as you get a balanced equation in the end, any method would work.
Okay, so you don't say in the exam use the, like for example,
No,
fraction. Okay,
that would be a little bit unnecessary. As long as you can balance the equation, that's more than okay.
Okay,
I'm
thank
just trying to show different methods, as students may find certain methods more useful for them.
you. Yeah, sounds good. Thank you.
Mhm. So we're already starting to see some proposed balanced equation coefficients. Let's keep working on this example for about another minute to a minute and a half, and then we'll discuss. And it's great to see all of these proposed responses in the chat and written out using the annotate feature. So let's now talk about this example. So there are two main methods that we can use. The first of which is the least common multiple method. If you're so inclined, you can complete this problem using the least common multiple method. We have 2 oxygens on the left, 5 oxygens on the right. We can cross our oxygen counts, And that can give us N2 gas plus 5O2 leads to 2N2O5. And now since we have 4 nitrogens on the right with only 2 on the left, we just put a coefficient of 2 in front of N2. And that gives us our balanced equation. So that's the least common multiple method, perfectly serviceable. The other method that we can use is the half notation method. So if we have 5 oxygens on the left and if we have 5 oxygens on the right and 2 oxygens on the left, what fraction can we guess that would give us 5? If we have 2 and we want 5, what fraction should we guess?
5/2.
Yep, exactly right. So we put the 5/2. Now, this equation is balanced in terms of atoms, but we're not quite done. We need to multiply this equation to get rid of our fraction. So what number should we multiply all of our coefficients by to get rid of our fraction? If we have a 2 on the bottom, what should we multiply all of our coefficients by to get rid of this fraction?
5.
2.
We'd multiply all of our coefficients by our bottom number, which is 2, as that would get rid of our fraction. Does that idea make sense? You find the largest number in our denominator for our fraction, and you multiply each of our coefficients by that number. So that in turn gives us a final equation of 2N2 plus 5O2 leads to N2O5. Does this idea make sense to everyone?
Yeah, I'm just a little slow at it.
No problem. Whatever method works best for you, that's the method I would encourage you to use. I just find that often students work best when they have an array of methods that they could use, and they can pick the one that suits the problem in their own preferences. Does this make sense to everyone? Perfect. So let's look at another example. This time we're asked to write a chemical equation from a sentence. This particular equation can be quite easily solved using half notation, but let's first start by just getting a unbalanced equation. So we have aluminum metal reacting with hydrochloric acid to give aluminum chloride and hydrogen gas. So let's start by getting out and writing an unbalanced chemical equation for the following reaction. And it's great to see that students are already providing their preliminary unbalanced chemical equation. I'll be rewriting and sharing the student responses that I've seen both in the chat and presented using the annotate tool. So we have the following proposed balanced equation. I'd like everyone to comment. Do your formulas for this unbalanced equation match? Do you have a different formula proposed? Do you have any questions in terms of getting the formulas for each of these different elements and compounds? And then I'd like you to take a look and start trying to balance this equation and comment on whether you agree or disagree with the proposed coefficients, whether you have a different set of coefficients. And I just want to emphasize, it's okay to disagree. I want as many students as possible to share their opinion and perspective on this example, so that way I can provide a more nuanced discussion as a class.
Professor, I have a comment about the acid. I think the one on the thing is hydrochloride. It's not hydrochloric.
Hydrogen chloride refers to the gas, while hydrochloric acid refers to the aqueous solution.
Oh, when it's aqueous, it's chloric, right?
Yes, yes, exactly right.
Okay, got it. Thank you.
So if we said aluminum metal reacts with hydrogen chloride, then we put a gas symbol, and that would be a slightly different reaction in terms of state symbols. Does that make
Hydrogen.
sense?
So if it was gas, we would say hydrogen chloride.
Yes, exactly.
Okay, got it.
Mhm. So in terms of the formulas for each of these compounds, they look great. To unpack how we obtained the formulas from our student responses, first, we have to remember the formulas of our elements. So aluminum is a metal, so we write aluminum just as an atomic species. Hydrochloric acid is derived from chloride, so we take H plus and Cl minus, we cross our charges and we get HCl aqueous. For aluminum chloride, we have aluminum 3 plus and Cl minus. We cross our charges and that gives us AlCl3. For hydrogen gas, hydrogen is a diatomic element, so that gives us H2 gas. So this is our proposed unbalanced chemical equation. Let's now try and count the atoms of each element on each side of this equation. And then what we can do is we can then adjust our coefficients to balance this equation. And I'd like you to write out your proposed coefficients for each of these chemical species in the chat. And if you have any questions, you can share your questions in the chat or verbally. This top response is that proposed by a few students in the chat, and I'd like you to try and balance this equation and then comment whether you agree with the proposed balanced equation, whether you disagree, whether you have any modifications, and if you have any questions, don't be shy to let me know. And just as a final note, make sure you check that the final equation is actually balanced. So we'll discuss this example in about 3 minutes. And don't be shy to share your proposed balanced equations in the chat or verbally. So we have the following student proposals in the chat for this balanced chemical equation. Does anyone have an alternative proposal for the balanced equation? Do you agree with the proposed balanced equation? Do you disagree? Let's try to share a little bit of our comments and we'll discuss in about another minute and a half. Okay, wonderful. So the student responses that I saw for this complete balanced equation were perfect. So we have 2 aluminum, 6 hydrogen. Well, we have for our preliminary before we add in our coefficients. Let's talk about the process for how we balance this equation. So we have aluminum, 1 hydrogen, and 1 chlorine on the left. We have 1 aluminum and 3 chlorines on the right, and 2 hydrogens on the right. So we're going to start by balancing all of our elements except our free element first. So we'll balance hydrogen last. So then to balance chlorine, I'm going to put a coefficient of 3. That gives me 3 hydrogens and 3 chlorines. Now I can use the half notation method, and I'm going to guess a coefficient that gives me 3 hydrogens, and that would be 3/2. Put what I want on top, and you put what you start out with on the bottom. Now that we have our fractional coefficients, we multiply our entire equation by the denominator to get rid of our fractions. And that in turn gives us the following complete balanced equation. Does this make sense to everyone? Does this idea make sense?
Professor, I have a question.
Please
When
go
we
ahead.
when we decide on what number we multiply it with, is it the highest number?
It's the largest number in
The
the
largest.
denominator.
Okay, got
Does
it.
that make sense?
Yeah, for some reason I thought it was the lowest.
Essentially, you multiply all of your coefficients to get rid of the denominator fraction.
Okay, thank you.
Perfect. Perfect. Okay, so let's keep going now and let's work on the following chemical equations. So we have zinc reacts with phosphoric acid to yield hydrogen gas and zinc phosphate. So let's try to write out the formulas and write out a preliminary unbalanced equation. Then, if you have your balanced equation already established, you can try and balance this chemical reaction by adjusting the coefficients. And we'll discuss the first part of this example, just getting our formulas established, in about 3 minutes. And let's try to get some proposed formulas shared in the chat or using the annotate tool for the following chemical equation. And we'll discuss in another 2 minutes. So we're already starting to see some proposed unbalanced and balanced equations. Let's write out the student proposed responses. So we have some student responses already shared in the chat, and these proposed equations look quite good. So let's talk about first just our preliminary equation. Before we balance anything, just where do we get these formulas from? So zinc is a metal, so it's drawn as an atomic species. Phosphoric acid is derived from phosphate, which is PO4 3-. We cross our charges with H+, and that gives us H3PO4. Hydrogen gas is written as H2, and for zinc phosphate, we know zinc happens to be a fixed charge transition metal with a 2+ charge. Phosphate has a 3- charge. We cross our charges, and that gives us zinc phosphate, which, interestingly enough, is an insoluble solid. Okay, so now that we have our preliminary unbalanced chemical equation, I'd like us to focus on balancing this chemical equation and adjusting the reaction coefficients. And we'll discuss this example in about another 2 to 3 minutes. And just so that way we can have a full discussion, some students have shared out the following proposal for this balanced equation. and you're more than welcome to share your own proposal for this balanced equation, as well as your commentary on whether the student proposed balanced equation, whether you agree with the student proposal, whether you disagree, whether you have a question or a modification. And we'll discuss this example in about another 2 to 3 minutes. And I really want to give as many students as possible the opportunity to share their opinion and perspective. So don't be shy to share your own questions or proposed responses for this example in the chat or verbally, and I'd be happy to get any of your questions answered. So we'll discuss this example and showcase the full solution in about 2.5 minutes. And we see some students voicing their agreement and also sharing their proposed balanced equation. Let's try to get a few more responses in the chat or verbally, and we'll discuss in another minute. Okay, so let's look at this example and let's work through this problem. So the student proposals look perfectly reasonable to me. So let's talk a little bit about the mechanics behind this example. So first we count our atoms of each element. So we have 1 zinc, 3 hydrogen, 1 phosphorus, and 4 oxygens on the left. And we have 2 hydrogens, 3 zinc, 2 phosphorus, and 8 oxygens on the right. So we're going to balance everything except hydrogen first. So let's start with phosphorus as it's found in the most complicated molecules. So to get 2 phosphorus on each side, what coefficient do I use?
2.
2, exactly. That in turn gives us 6 hydrogens, 8 oxygens, and 2 phosphorus. So we see phosphorus and oxygen are now balanced. Give me one. Oh, never mind. That problem fixed itself. Okay, perfect. So now to balance zinc. In order to get 3 zinc on each side, what coefficient do I need in front of zinc? One times what would give us 3?
3.
3. Yep. Perfect. And now to balance hydrogens, if I have 6 hydrogens on the left, 2 times what would give us 6? What coefficient do I need in front of each 2? 3. Exactly right. And that gives us our final balanced chemical equation. Does this idea make sense to everyone? Is everyone comfortable with this example? Okay, so let's keep going now. And let's try to balance the following chemical equation, and you're welcome to use any method. So this is sort of a capstone. These are examples similar to what you'd see on an exam. So let's look at the following example and let's try to quickly balance this equation using any method that we have access to. So given the coefficients A, B, C, and D, let's try to fill in our balanced equation coefficients, and we'll discuss this first example in about another 3 minutes. And it's great to see that we already have some proposed responses for our balanced equation coefficients. Let's give students a little bit more time to contribute their responses, and then we'll discuss in another minute. Okay, so let's discuss this example. So in our counts, we have, whoops. So in our counts, we have 2 nitrogens and 2 hydrogens on the left. And we have 2 nitrogens and 4 hydrogens on the right. In order to balance hydrogen, we need to guess a coefficient. So 2 times what would give us 4? What coefficient do we need for H2? 2. Yep, exactly. Because 2 times 2 gives us 4. And now we have our complete balanced chemical equation. Any questions on this example? Any questions on this example? Okay, so let's work on another example. This is another very common type of reaction that you'd see. So given the following chemical equation, I'd like you to fill in the coefficients for each of the chemical species in this equation. And we'll work on this example for about 3 minutes before we discuss. And I'd like to see some student responses in the chat so that way I get a sense of how students are progressing through this problem. And we're already starting to see some proposals in the chat, but it's okay. Just keep working through the problem and sharing your responses. And I'd be happy to communicate and share your responses with the rest of the class. And if you have any questions on this example, don't be shy to ask it verbally or in the chat. And it's great to see that we have a range of student responses submitted for the following example. And we'll take about another minute and then we'll discuss. Okay, so let's discuss this example. So in this case, we have 1 calcium and 2 chlorine on the left. We have 1 silver, 1 nitrogen, and 3 oxygen on the left. And we have 1 silver, 1 chlorine on the right, 1 calcium atom on the right, and 1 nitrogen atom and 3 oxygens on the right. So looking at this equation, we're going to first need to balance our unbalanced element, which is chlorine. So then, what coefficient do we need to multiply by to get 2 chlorines? 1 times what would give us 2? What coefficient do we need for silver
2.
chloride? 2. That gives us 2 chlorines and 2 silver. And now in a similar vein, in order to balance silver, 1 times what would give us 2?
2.
2, exactly. So that gives us 2 silver, 2 nitrogen, and 6 oxygen. Now to balance nitrogen, what times 1 would give us 2 nitrogens and 6 oxygens? What times 1 would give us 2?
2.
2. There we go. And that gives us our complete balanced chemical equation. Does this idea make sense to everyone? Any questions on this example? Okay. So let's look at an example of a combustion reaction where half notation will be quite useful. So given the following coefficients, A, B, C, and D, I'd like us to work on balancing this chemical equation and filling in our balanced equation coefficients. This example is a little bit more difficult than the previous ones that we've looked at, but nothing that you aren't more than capable of handling. So let's try to balance this somewhat more complicated example, and we'll discuss in about another 3 to 4 minutes. And I'll be checking the chat and students writing on our class whiteboard for any potential responses that I can share out with the rest of our class. And so we have our proposed balanced equation coefficients drawn out using the annotate tool. It's great to see. Let's give students a little bit more time to work through this example, and let's try to get a few more student responses and contributions, and we'll discuss in 1.5 to 2 minutes. So we have some additional proposed responses for this balanced chemical equation in the chat. Let's keep working on this example, and then we'll discuss momentarily. And this may be a good place to try utilizing half notation as we have an isolated pure element. And we'll discuss this example in another minute. Let's try to get a few more student responses, or if you have questions, I'd be happy to address them. Okay, so let's talk about this example. So in terms of our counts, we have 1 nitrogen and 3 hydrogen on the left, and we have 2 oxygens on the left as well. On the right, we have 1 nitrogen and 1 oxygen from nitrogen monoxide, and we have 2 hydrogens and 1 oxygen on the right from water. So then let's start by balancing nitrogen. Nitrogen's balanced, so that's all good. Hydrogen is not balanced. So what we're going to do is we're going to use the least common multiple method to balance hydrogen. So that gives us the following first adjustment for our coefficients. So we have 2 ammonia plus oxygen gas leads to nitrogen monoxide gas plus 3 H2O. Now we're not quite done because we have 2 nitrogens, 6 hydrogens, and 2 oxygens on the left. And we have 1 nitrogen, 1 oxygen, 6 hydrogens, and 3 oxygens on the right. So in order to balance nitrogen, what we're going to do is we're going to guess and place a coefficient for nitrogen monoxide. So 1 times what would give us 2 nitrogens? What coefficient do we need for nitrogen monoxide?
2.
2, yep. That gives us 2 nitrogens and 2 oxygens. So in total, we have 5 oxygens on the right. And now here's where we can utilize half notation. 2 times what would give us 5? So what fraction if we put
5 over 2.
5 over 2, exactly right. This gives us our preliminary balanced equation. And now what we do is we multiply all of our coefficients by our denominator, which is 2. That in turn gives us 4 ammonia plus 5 O2 leads to 2 nitrogen monoxide plus 6 water. So as you see, I really like this example because it lends itself well to utilizing multiple balancing methods at once. Does that make sense to everyone? Does this idea make sense? Does this problem make sense once we've gone through it together as a class? The student responses that I've seen looked great so far as well. As long as you take things step by step and you count your atoms each time, you'll eventually reach your balanced equation. Any questions on this example? Okay. So let's keep going now. We're systematically looking at a lot of common reaction types that you'll see later on in this class. So let's try to balance a textbook set of decomposition and combination reactions. These are two reactions that are related in terms of classification. The top reaction is known as decomposition. The bottom reaction is known as combination or synthesis. So I'd like you to work on balancing these two equations. And I'd like you to share your proposal for the reaction coefficients in the chat for each of these two examples. And I'll give everyone about 5 to 6 minutes to work on these two examples. And I'd be happy to answer any questions and convey any student responses that I see to the broader class. And we'll discuss these examples in about 6 minutes. Practice makes perfect. You're going to need to be able to write and balance chemical equations in order to handle the next topic in this chapter, which is stoichiometry, which involves performing calculations given a balanced equation. So let's work on these examples. Don't be shy to share your responses in the chat or verbally, and then we'll discuss in about 5 to 6 minutes. And we have some students proposing the following coefficients of 1, 1, and 3. You're also welcome to comment whether you agree or disagree with the student proposed coefficients. And we'll discuss both of these examples in about another 4 to 5 minutes. Additionally, we see further student proposals for the second equation of the following three coefficients. So these are our student proposed reaction coefficients. I'd like you to continue working on balancing these equations and then comment whether you agree, whether you disagree, whether you have a different balanced equation, or whether you have a question that you'd like addressed for the following two examples. And we'll discuss these examples in about 3 minutes. And we see a pretty consistent consensus among the student responses. Let's now discuss this example in about another 1.5 to 2 minutes. And if you have any questions working through these examples, or if you have an alternative proposal, don't be shy to ask. Okay, so let's discuss this example. The student proposals look perfectly reasonable. So let's talk about the mechanics behind balancing this equation. So first, we're going to focus on our atom count. So we have 2 aluminum, 3 carbons, and 9 oxygens, remembering the subscript applies to everything in the parentheses. For aluminum oxide, we have 2 aluminum and 3 oxygen. For carbon dioxide, we have 1 carbon and 2 oxygen. We're going to balance carbon first. So what coefficient do we need to guess in order to have 3 carbons on each side?
3.
Yep. So we need a coefficient of 3. That in turn gives us 3 carbons and 9 oxygens on each side, as well as 2 aluminum. So this first equation is just balanced with a single coefficient. We've actually seen an example of this reaction when we talked about our section titled Chemical Reactions and performed the lab titled Chemical Reactions. Let's look at the second example, which is really carried by this idea of half notation. So we have 2 aluminums and 3 sulfurs on the right. We have 8 sulfurs on the left and 1 aluminum on the left. So first we're going to balance aluminum by adjusting our coefficients. 1 times what would give us 2 aluminum? 1 times what gives us 2?
4. What 2?
2, yep. Okay. So next, if we have 3 sulfurs, on the right and 8 sulfurs on the left, what fraction can we put to give us 3?
8/3.
Yep, 3/8. And in turn, now that we write in our preliminary fractional balanced chemical equation, we then can multiply all of our coefficients We then can multiply all of our coefficients by our denominator. And our denominator in this case is 8. So that in turn gives us 16 aluminum plus 3S8 plus 8 aluminum sulfide. Does this example make sense to everyone? Does this example make sense?
Professor, what? Oh, wait, never mind. That says solid.
Yes. Is there a question? Please don't be shy to ask. Is
No,
there?
I just didn't know if that was an S at the end of the.
Yes, there we go. Sorry about that. Perfect. So this is a great stopping point for today. I'm really pleased at how the class progressed through these balancing chemical equations examples. These will be a centerpiece part of your second exam, analyzing formulas, writing formulas, and balancing equations. So if you can do the examples that we've outlined in the notes, you'll definitely see a few examples similar to this on your exam. So this is a great stopping point for today. So what we'll do is we'll take a quick break and then we'll resume for laboratory at 12 o'clock.